9.10 Lesson 2, Taylor and Maclaurin series. Our objectives for today are 1 and 2, which we actually did yesterday, and 3, which we will do today. So yesterday, in Lesson 1, we used the definition of Taylor series to form a Taylor series centered at 0 from the function f of x is equal to sine x. That was example 1 from yesterday's lesson, lesson 1. And then yesterday, we used the ratio test to determine the interval of convergence for the Taylor series from objective 1. And we did that yesterday during lesson 1, and we found that the interval of convergence for that Taylor series was all real numbers. The question arises, does that Taylor series that we found yesterday converge to the function from which it was derived for all real numbers x? In other words, how do we know that the Taylor series centered at 0 that we derived yesterday from the function sine x using the definition of Taylor series, how do we know that that Taylor series on its interval of convergence, which was all real numbers, will in fact be an exact representation of the function f of x is equal to sine x? That's the question that we want to consider today. And we'll be looking at objective 3. But first, I want to address the issue of why you might have a Taylor series that does not necessarily converge to the function from which it was derived on its interval of convergence. So we look at figure 9.23. And in black, we see the graph of the function f of x, which is a piecewise defined function. The rule for f of x is sine x for x values between negative pi over 2 and positive pi over 2. But if x is less than negative pi over 2, the function is a constant value of negative 1. So you can see that here if I extend the graph. And for x values that are greater than pi over 2, the function f is a constant value of positive 1, and you can see that here as I extend the graph. So what does this have in common with the function that we worked with yesterday? Well, we worked with the function f of x is equal to sine x yesterday for all real numbers. So that was our function yesterday, and that is represented in red here. What does it have in common with the function from figure 9.23? Well, it's the same rule, sine x, but the function from figure 9.23 only uses that rule on the interval from negative pi over 2 to positive pi over 2. So yesterday, we derived a Taylor series centered at 0 for the function f of x is equal to sine x. If we were to instead derive the Taylor series centered at 0 for the function f of x from figure 9.23, we would in fact get the same Taylor series. Why is that? Because how do you form the coefficients of the Taylor series? You evaluate your function at the center and you evaluate its derivatives at the center. And the center was 0, and of course the function from figure 9.23 and our function from yesterday at 0 is the same rule. So that is why we would have the same Taylor series both for the function that we worked with yesterday and for the function from figure 9.23, because they have the same rule at x is equal to 0. So when you're forming the Taylor coefficients and when you're evaluating the derivatives of the function at 0, you'd get the same values for both what we did yesterday and for the black graph that we're looking at in figure 9.23. And because you get the same Taylor series, when you use the ratio test to determine the interval of convergence, you will in fact get that both series, because they're the same, will have a radius of convergence that is infinity. In other words, both series will converge for all x, but both series cannot converge to the functions from which they were formed, because they were formed from different functions. So how do we know that a particular Taylor series formed from a function will converge to the function from which it was formed for all values x? That is objective 3 that we want to work on today, and there is a theorem that will allow us to make that conclusion by using the theorem. To drive the point home, I want you to look at figure 9.24 from your textbook. And again, yesterday we worked with the function f of x is equal to sine x. And we came up with our Taylor series centered at 0 for f of x is equal to sine x. And we found, using the ratio test, that the interval of convergence was all real numbers. And in fact, today we're going to show that that Taylor series that we found in example 1 yesterday will in fact converge to the function from which it was formed, f of x is equal to sine x, on its interval of convergence. And figure 9.24 shows you what we call partial sums of the Taylor series. The first few terms of the Taylor series derived from f of x is equal to sine x. And you can see here we have the first degree Taylor polynomial, and that's the graph will be a line. And you can see that it does a decent job of approximating the function sine x for x values that are close to 0. Now when you have a third degree Taylor polynomial, it does a better job for a larger range of x values centered at 0. Here you have a fifth degree Taylor polynomial. It does even better than the third. And here you have the seventh degree Taylor polynomial, and it does even better than the fifth degree Taylor polynomial. And we're saying that if you have the Taylor series, which has infinitely many terms, it will in fact be an exact representation of the function sine x for all real numbers. But the reason why we need to go through the lesson that we're looking at today is because we could have a situation like the function represented by figure 9.23, which has the same rule as the function that we worked with yesterday at x is equal to 0. So when you try to form the Taylor series for this function, you will in fact get the same one that we got yesterday, and it will have the same interval of convergence, all real numbers. But that Taylor series will not converge to the function from figure 9.23 because it's different from the graph of the sine function outside of the interval from negative pi over 2 to positive pi over 2. And that is why we need to go through the lesson for today to have some way of knowing that, let's say we, step 1, derive a Taylor series centered at c for some function f, and step 2, we determine the radius of convergence for that Taylor series. Step 3 is what today's lesson is about. How do we know that that Taylor series on its interval of convergence will converge to the function from which it was derived? Here is how we're going to know. We're going to use Theorem 9.23, which is about convergence of Taylor series, to show that the Taylor series derived from a function, such as what we did yesterday, will in fact converge to the function from which it was derived on its interval of convergence rather than some other function. So we take a look at Theorem 9.23, convergence of Taylor series. And to help us understand that, we will take a look at Theorem 9.19, Taylor's theorem that we studied in section 9.7. In section 9.7, we learned about Taylor's theorem. It states that if a function f is differentiable through order n plus 1 in an interval I containing c, then for each x in the interval, there exists z between x and c, such that the function's value at x will be equal to the nth degree Taylor polynomial approximation's value at x plus the remainder, where the remainder So this is our approximate value. This is the remainder. And this is our exact value. And Taylor's theorem states that the remainder is equal to the n plus 1th derivative evaluated at z, where z is between x and c, divided by n plus 1 factorial times x minus c to the n plus 1 power. So this remainder is the difference between the exact value of the function at x and the nth degree Taylor polynomial approximation for f at x. So this is the difference between the two. The remainder is the difference between the exact value and the approximate value. And now look at Theorem 9.23. It states if the limit of r sub n, and r sub n is talking about this from Taylor's theorem, if the limit of r sub n as n goes to infinity, and what is n? N is talking about the degree of your Taylor polynomial. So the higher the degree, that's what we mean by n going to infinity, n approaching infinity. If the limit of the remainder as n goes to infinity is 0, in other words, here's how you should think of it. The remainder is the difference between the exact value and the approximate value. If that remainder is going to 0 as the degree of your nth degree Taylor polynomial is increasing, that means the greater the value of n, the lesser the difference between the exact value for the function at x and the approximate value for the function at x. Okay? So that's what it means for the remainder to go to 0 as n approaches infinity. And Theorem 9.23 says, if the limit of r sub n as n goes to infinity is equal to 0 for all x in the interval I, then the Taylor series for f converges and equals f of x. We say Taylor series because we no longer have an nth degree Taylor polynomial, because what is going on with n? N is going to infinity. So what you have here with the nth degree Taylor polynomial is what we call a partial sum. What we have here is a partial sum of the infinite series. But what you have in Theorem 9.23 is the infinite series itself. But you want to understand this statement as I just stated. If the limit of r sub n as n goes to infinity is equal to 0, and again, what does that mean? The difference between the exact value of the function and a partial sum approximation for it is approaching 0. The difference between the two is approaching 0. For all x in the interval I, then we say that the Taylor series for f will converge to the function from which it was formed. The proof of Theorem 9.23 is in your textbook. It's actually not that hard. And when we explained Theorem 9.23, in fact, the proof is using that idea that we just explained, but putting it in mathematically precise formulation to write a formal proof of the theorem. Example 2. Show that the Taylor series centered at c is equal to 0 for f of x is equal to sine x converges to sine x for all x. So yesterday during lesson 1, we derived the Taylor series centered at 0 from the function f of x is equal to sine x using the definition of a Taylor series. And yesterday during lesson 1, we used the ratio test to determine the interval of convergence for this Taylor series. Today, we would like to use Theorem 9.23 to show that the Taylor series from yesterday will in fact converge to the function sine x on its interval of convergence. In other words, that this power series will be an exact representation of the function sine x for all real numbers. And to do that, we're going to use Theorem 9.23. So what we have to do is we have to consider what happens to the remainder from Taylor's theorem as n goes to infinity. And we have to show that that remainder will go to 0 as n goes to infinity. If we can show that, then we may conclude by Theorem 9.23 that the Taylor series that we found yesterday will in fact converge to the function sine x on its interval of convergence, which is all real numbers. So here's Taylor's theorem, and we remember the formula for the remainder from Taylor's theorem, where z is between x and c, c being the center of the Taylor polynomial, or the Taylor series, as we're doing today. But more importantly, something else that we did in section 9.7 as we were working with Taylor's theorem was to put an upper bound on the error. We call this the remainder, but if we put absolute value of r sub n of x, the absolute value of the remainder is called the error. And with z being between x and c, we don't have an exact value for the n plus 1th derivative of f evaluated at z. But what we can do is we can put an upper bound on what this could be. And that would basically say that the error has to be less than or equal to the most it could be. So we're going to have what you see here, that the upper bound for the error has to be less than or equal to, again, the error is the absolute value of the remainder, and you're just saying, let's put absolute value, and let's make the error the largest it could be, so that we would have an upper bound for the error. So you basically want to find the maximum value of the n plus 1th derivative evaluated at z, where z is between x and c. And you would like to put absolute value on x minus c, and then you have n plus 1 factorial, which is already positive. So that's what we have here. So again, we have to look at r sub n of x, and we have to show that the limit of r sub n as n goes to infinity is equal to 0. And to help us do that, we're going to use what we learned in section 9.7, along with the squeeze theorem for finding limits. So our objective in using Theorem 9.23 is to show that the limit of the remainder r sub n as n goes to infinity is equal to 0. So using Taylor's theorem, we know this to be the remainder. We can put an upper bound for the remainder by choosing a value of x that would give us the maximum value for the n plus 1th derivative evaluated at z. So what we need to show is that this remainder r sub n as n approaches infinity will be equal to, will go to 0. So we can put bounds as follows. One thing we can note is that our function is, of course, the function that we began with. F of x is equal to sine x. And if you consider the derivatives of this function, the first derivative is cosine, the second derivative is negative sine, the third derivative is negative cosine, the fourth derivative is sine. And you can see that there's a cycling here, because by the time you get to the fourth derivative, you get back to the original function. So the fifth derivative will be cosine, the sixth derivative will be negative sine, the seventh derivative will be negative cosine, and the eighth derivative will be sine, and it will just repeat, it will just cycle forever. So the derivative of f for any order will be either positive sign, negative sign, positive cosine, or negative cosine. And in Taylor's theorem, we know that z is between x and c. And for our problem, the center of our Taylor series is at c is equal to 0. And because from our lesson yesterday, we found that the interval of convergence for this power series is all real numbers, x can be any number. X can be any number that you choose. It could be, for example, 20 trillion pi, whatever. X could be any number. So z could be basically any number. But we do have something to work with because we know that the n plus 1th derivative of our function f of x for any n, for any z, can be no greater than 1. Because whatever order of derivative you have of the function f, it will be one of these four functions. And these four functions, evaluated at any input, can be no greater than 1, because 1 is the maximum output that is possible for any of these four functions. So that is allowing us to say that the biggest this could be for any derivative at any z is 1. So that really allows us to simplify our work by just recognizing that that is going to be 1. So now we have just this. And what we have to show is that, first of all, the remainder is going to be non-negative. So the remainder is going to be greater than or equal to 0. The absolute, I meant to say the error is non-negative. So the error, which is the absolute value of the remainder, will be greater than or equal to 0. And it is going to be less than or equal to this quantity here. And we know that c is equal to 0, so we're going to have the absolute value of x minus 0 to the n plus 1 power over n plus 1 factorial. And what we're trying to show, again, is right here. This is what we're trying to show, that the limit of the remainder as n goes to infinity is equal to 0. Well, we can show that the limit of the error as n goes to infinity is equal to 0 as follows. This error is bounded between 0 and this quantity, and the limit of 0 as n goes to infinity is 0, because 0 is just a constant, there's no n there. And the limit of this quantity, the absolute value of x to the n plus 1 power divided by n plus 1 factorial as n goes to infinity, is also equal to 0, because in the denominator you have a factorial function, and in the numerator you have a power function of where the variable is n. So factorial functions have a faster rate of growth than power functions. Actually, it would be not a power function, but an exponential function of n, because the variable n is in the exponent. But regardless, factorial functions have a faster rate of growth than exponential functions. In the numerator, you have an exponential function because the variable is in the exponent. But because factorials grow faster than exponential functions, the limit of this quantity as n goes to infinity will be 0. So what we have is the following. So we're using our compound inequality that we have here, in which the error is bounded between 0 and this quantity. And as we can see from the reasoning that we just discussed, the limit of this quantity as n goes to infinity is 0, and the limit of the constant 0 as n goes to infinity is 0. And because the error is bounded between 0 and this quantity, and the limit of the boundary, the limit of 0 and this quantity as n goes to infinity are both equal to 0, by the squeeze theorem, the limit of the quantity that is bounded between those two quantities as n goes to infinity must also be equal to 0. And if the error is going to 0 as n goes to infinity, so will the remainder. And that's what Theorem 9.23 is talking about. If the remainder as n goes to infinity is 0, then what can we conclude by Theorem 9.23? We may conclude by Theorem 9.23 that the Taylor series formed from the function f of x is equal to sine x, the Taylor series centered at c is equal to 0, formed from the function f of x is equal to sine x, will converge to the function f of x is equal to sine x on its interval of convergence, which we found yesterday to be all real numbers. In other words, we have just verified using Theorem 9.23 that the Taylor series centered at 0 that we found yesterday will be an exact representation of the function f of x is equal to sine x for all x that are real numbers. As we saw at the beginning of the lesson, what that means is that Taylor series, that infinite Taylor series, will be an exact representation of the function sine x for all real numbers x. And if you have partial sums of that infinite Taylor series, such as the 7th degree Taylor polynomial here, it would be an approximation for the function sine x. But the infinite Taylor series will be an exact representation of the function sine x. So today we looked at lesson 2, and our objectives were 1 and 2, which we saw in lesson 1, use the definition of Taylor series to form a Taylor series centered at c is equal to 0 from the function sine x. And yesterday we used the ratio test to determine that the interval of convergence for that Taylor series was all real numbers. And today we looked at showing that that Taylor series will be an exact representation for the function from which it was formed on its interval of convergence by using Theorem 9.23. And as a part of this lesson, we discussed why that was necessary. So use Theorem 9.23, convergence of Taylor series, to show that the Taylor series from objective 1 converges to the function from which it was formed on its interval of convergence. So as a summary, these are the guidelines for finding a Taylor series. 1 is objective 1. Basically, you want to find the Taylor series for a particular function by using the definition of Taylor series. Differentiate the function several times and evaluate the function and each of its derivatives at c so you can form the Taylor series using the definition. You want to then determine the interval of convergence for the resulting power series, and we looked at 3 today using Theorem 9.23 to help us. Within the interval of convergence, determine whether or not the series formed from the function will in fact converge to the function from which it was formed. Will it be an exact representation of the function on its interval of convergence? And as you may recall from the early part of the lesson, we looked at figure 9.23 and compared that to the function f of x, and basically that was to help you understand why this is necessary.